Hey guys, it's Michael again with Breaking Concepts, and welcome to today's part 2 video of equilibria of recursive sequence and cobwebbing. So today we're actually going to take a look at cobwebbing with allele effects. Absolutely, you're in the right spot. If you remember last time from part 1, we kind of took a look at this graph here. So today, our objective here actually is to explain how we actually get this curve and what other implications is this graph. And this is such an interesting topic today, especially combining with what we're going to talk about, the allele effect. And it's going to be very helpful when it comes to population mapping and ecology and so on and so forth. So without further ado, let's dive right into it. So here, the actual name for the entire thing is called the Discrete Logistic Growth Model with Strong Allee effects. And by the way, I remember last time I actually didn't show you the entire full picture of the graph. Here is the full picture of the graph. And you can see that after B, the entire graph just kind of goes straight for a deep plunge, right? We can see that I kind of quote that in the area of C here, okay? So, throughout the graph, we have 4 very special points. We have number 1 is the 0 point, where I've kind of marked in red here. 0 is our stable equilibrium. We've kind of talked about stable and unstable equilibrium from our last video. And A is going to be our unstable equilibrium, right? And B is going to be our second stable equilibrium, as well as, now you guys know there's a part C where the entire graph takes a deep plunge. Quick refresher. Let me just do a quick cobwebbing here just to prove that this is what happened. So if I start from here, I will get something around here. So you can see that we're pushing towards 0 away from A. And if I start from here, we're going to see that we're going to get something like this. So we're pushing towards B and away from A. So in general, you can see something like this, right? Pushing away from A towards B or 0. So let's talk about what B is. From the way we construct this equation, actually from last video, probably you guys could already seen that or kind of know that. B is actually our carrying capacity. And carrying capacity basically says is the population where the habitat is at max. Using our fish and pond example from previously, the maximum of the pond maybe is 3, and 3 is a maximum carrying capacity. So if we add more, fish is going to die. If we have less than the carrying capacity, then population is going to go, the population to keep creeping back towards our B, right? So this is the idea of carrying capacity. Okay, so here's the idea of allele threshold. It is a new concept that we didn't talk about last time, and we're just going to go through it with you guys here. Super simple. So allele threshold, you can kind of think about is the minimum population required in order for species to survive. So if you reach below, we have a maximum threshold, and this one you can think about is the minimum threshold. So we can say this is the max, and this is the minimum, okay? So if we're below this minimum threshold, the population number 1, they're not going to be having enough mates to survive, or number 2, they don't have enough people or group to survive any predator attacks, or even successfully hunt. So what eventually is going to happen is going to lead them to an extinction. I mean, since primary school, we've talked about endangered species. This is kind of what I mean by that, right? If they're falling below a certain critical threshold, this is when scientists becomes a lot more serious, a lot more worried and stressed about a certain type of species facing extinction. And so C is actually what we call the immediate crash. So you can see that there's a huge plunge from B onwards. So what happened is what we're facing is called the immediate crash. So let's take a look at here, right? If a habitat is comfortably can only hold 100 fish, and you suddenly, let's say, for whatever reason, you cramp 10,000 fish, what do you think is going to happen? So the crash would happen because the O2, like the oxygen, is going to be depleted within hours, or if we're talking about at this scale, probably within minutes. And toxic weight is going to build up. We talked about ammonia. Imagine a capacity at 100 and now we have 10,000. The ammonia concentration is going to be so toxic that no fish is going to be able to survive. And so it says by tomorrow here, but I think, within hours, the population will not drop gracefully, but do a steep plunge to 0. So remember how we look at this graph. We want to find the current XT, the current population. And let's say our population is actually right here. So from the graph, by tomorrow, so let's say our population is somewhere around here, suddenly is somewhere around here. And from the graph, we know that by tomorrow, we're going to probably have only maybe 1 or 2 fish left in the population. So this plunging to zero basically guarantee that when the population suddenly becomes very enormous, way ahead of what we can contain, what the carrying capacity can contain, then there's probably a really high likely chance that the entire population is going to go extinct by tomorrow. So here I'm just going to hide myself for maybe 1 or 2 seconds. You can pause the video if you like. Just take a quick screen capture. Some of you may be asking me this question. Okay, cool. We know that xt plus 1 versus xt is going to show you a graph like this, right? And even the drop, right? How do you actually get this graph? It doesn't really make sense intuitively. If you just look at the formula or the equation, we get something like an xt plus 1 equals to fxt, or even if you want to write something as is xt plus gxt. So remember, this is our updating function, and this is our difference equation. It doesn't intuitively make sense. So how do we actually get this curve? Well, think about this. F equals to ma. We've learned this throughout high school physics, right? F, at the same time, also represents mgm over r squared, right? So basically, it's to find what is the actual definition of f, which also translates here. We want to find what is the actual definition of our difference function here to give us this curve. Okay, you guys ready? We're going to go right into it. So here's our first step. We have 3 steps in total. First step, we're going to take a look at the logistic growth. The simplest rule for growth, as you can see here, factors in 2 things. So the first thing we need is birth, right? In order for populations to grow, we need to have more babies, more population, right? So it is proportional to our current population, basically our x, right? Proportionality constant times x, and r is basically our growth rate. And number 2 is actually you have to factor in competition. Competition is important because you're going to fight for resource, you're going to fight for a lot of things, right? So we have to factor in that one. Competition is actually proportional to crowding. And what crowding does is that it will actually affect the intensity of the fighting. Imagine the more people is fighting for the same resource, the higher, the more intensity, right, the fight is going to be. And let's say we have a lot of the same amount of people, but we have ample of resource. The probability that they're going to fight is going to be way less than the previous case. And so here, we can see that competition depends on intensity, and intensity and all depends on 2 things. Number 1 is our birth rate again, right? Because if a species produce very rapidly, that means more people are going to come to the population. More people are going to come to the population, then there's a high likely chance that they're going to compete, and there's a more likely chance that they're going to compete. So that increases competition. And number 2 is our carrying capacity. So like I just mentioned, right? If our carrying capacity is tiny, right? We don't have enough resource for everyone, and we're so scarce, then resource is scarce, then bumping into someone is going to be dangerous. Intensity of the fight is going to be way higher. So the penalty is what we call penalty should be very large. So our equation for competition is going to be r over k times x squared. Well, it is x squared because of competition. There are x individual that can start a fight with each of the x individuals. So together, you just got to multiply by them, but basically it's x times x, which is our total potential collision, and therefore we have x squared. Again, from this equation, we know that r increase as the birth rate increase, there'll be more competition, right? As the x squared increase, right, which is our population increase, there's more potential collision, and k, the reason why is 1 over k is because as k is small, then the fraction is big, okay? Conversely, if k is large, then the fraction is small, right? If k is large, meaning there's more available resource, then the competition is going to be a little bit lesser, right? I hope that makes sense. So combining this this one, and this one, our logistic growth is going to be, gx equals to rx, which is the birth, minus our r over k x squared. The competition is going to decrease the amount of population because of death, birth, minus competition. And if we do some manipulation, we can actually take out x and r from inside. And after doing some manipulation, we take out r and x, we have 1 minus x over k. There we go. This one is gx. And we've seen this a lot of times before. Another way to kind of interpret this one is 1 minus x over k if x approaches K, our carrying capacity, is going to be 1 minus 1. 1 minus 1 is 0. The entire, growth the gx just becomes 0. There will be no growth. Even though we're not finished, we can see that our first step from our logistic growth, that this entire equation is a quadratic equation. It has a negative x squared, which means it has an open downward curve. And let's look at what happens if our K is 10. Let's say our maximum capacity is 10. So we know that our Gx is going to be equal to our Rx times 1 minus x over, we see 10 here now, over 10. In order to find this number here, all we got to do is make Gx equal to 0. We have 0 Rx times 1 minus x over 10. This one represents x equal to 0, and we already have this here, so we don't have to worry about this one. So now we want to worry about this one. I'm going to use a different pen. So we have 1 minus x over 10 equals to 0. And here we do some manipulation, we'll find negative 1, negative x over 10, and so x eventually is going to be 10. 10, which is also our k, so we can see that our x-intercept is actually our carrying capacity k. So here we have xt plus 1, xt. So this is the first step of crafting the equation. We have the Allee effect, which defines the equilibrium A. It is unstable, but it is the minimum population required for a population to survive. So basically what this means is that if our population is below A, they're going to die. It's going to go to extinction. And if they are above A, that's when they can survive. And if they're on A, that's our equilibrium. And technically, at equilibrium, the Gx is equals to 0. So how do we craft such a limitation using our population and our equilibrium A? So all we have to do is just have x, our population, over A minus 1. So we can see if x is less than A, then our x over A minus 1 is going to be less than 0, which means it will turn our entire Gx equals to negative, which means basically, if our Gx is negative, this means that we're dying more, we're losing more population. Our death rate is going to be higher than our birth rate. Then the new population would be less. All right, so here's the Allee effect. And all we gotta do is to put this Allee effect into our previous equation. We're gonna have something like this. Gx equals to Rx times x over A minus 1. Again, this is our Allee effect, and times 1 minus x over k, that's the competition. And I hope that makes sense to you. Now, we can implement this in our updating function. It's going to equals to our f xt, which is our updating function, equals to our rxt plus our gxt, and so we have xt plus rx x over xt over a minus 1 times 1 minus xt over k. And make sure you know that this is actually a cubic function, and therefore we will see an undulation and kind of goes down. So all in all, this is our discrete logistic model with strong Allee effects, and this is the reason why we get this undulation. So I hope this makes sense to all of you so far. Stay tuned for part 3, where we're going to talk about more about equilibrium and cobwebbing. Thank you.